Hello, hello, and welcome back to the start of a new chapter. We're getting into chapter 14 here. We begin with a discussion of vector-valued functions. This is going to be our primary thing that we're studying in chapter 14, the vector-valued functions. So we'll introduce these here in section 14.1. Then we're going to introduce calculus into the situation. So we're going to be differentiating and integrating these vector-valued functions and interpreting those results. Once we have that, now we can talk about motion in space. And again, we're in 3 dimensions now, and so there's going to be some new things that come up when we have a particle moving in 3 dimensions. So we're going to get into that in 14.3. 14.4 is sort of kind of a utility section. Here we'll answer questions like how do we determine the length of a curve drawn out in space, so the distance traveled by an object moving in 3 dimensions, when it's not so easy to figure that out, right? Not along a straight line, or not just, in a circle, something like that. More complicated curves, how do we determine the length of them? And then 14.5, as I mentioned, this motion in space, it's going to turn up a lot more things because we're moving in space. One of these new sort of things to study is curvature and normal vectors. So we're going to get into those as well. By the end of this chapter, you should have a lot more, or a lot better of an understanding of how objects move through 3 dimensions. And likely you'll encounter some things you have not seen before. So pretty exciting stuff. Let's start this video with just introducing some vector-valued functions. So what are vector-valued functions? Oh, when we see vector-valued, what we're talking about is the output of the function. This is the output, right? And you can notice that because we're saying vector valued. So the value of these functions, the output of them, are vectors. That's the idea. So we're going to input real numbers. So input a real number. I'll just say real number with a capital. A real number. We'll call that a parameter. A lot of times we can think of this like time, and we output a vector. So at every point in time, we have this vector. Now, one way to think about this is an object moving in space. So the idea is we input some time, some parameter. The output is a vector. And if we think of that vector as being a position vector, so whose tail is at the origin and whose head points at the object, then the output of all these vectors determine a curve in space that the object is tracing out. So that's the idea with these, right? Tail at the origin, head at the location of the object, and this is going to change over time. So the curve, or the vector, position vector, is going to trace out the curve of the object. And so what do these look like? Well, we have r of t, notice the boldface here, or an arrow over it, r of t, that's telling us it's vector valued, the outputs are vectors, and then we'll have a function for the x component, y component, and z component. So we'll see that these vector valued functions are sort of, or can be thought of as, if we're in 3 dimensions, as 3 scalar valued functions. So each of these is scalar valued. And then we put them together in with the components of a vector, and we get the vector that comes out. So that's the idea. And these each depend on a single variable t. So you actually have encountered something very similar to this before, again, back in Calculus 2 in chapter 12. These are introduced, and that's parametric equations. So remember, with parametric equations, we have something that looks maybe like this: x of t, y of t, z of t. So right, we have an x coordinate, y coordinate, z coordinate, and each of those depends on a time value t. So these parametric equations, if we sort of take the x, the y, and the z parts of that parametric equation, and we stuff them inside of a vector like this, what we get is a vector-valued function. So it's really just another way to kind of think of a set of parametric equations. The key difference here is with the parametric equations, we're talking about points in space, right? The output are points in space that look like x of t, y of t, z of t. We get points out of this, whereas with vector-valued functions, we get vectors out, which means we can use all those lovely operations of vectors on the outputs of these functions. So it gives us a lot more structure to work with, and that's going to come in handy, especially when we introduce calculus into this. Right, so this is the idea. From a parametric equation, we can form a vector-valued function like this, and from a vector-valued function, we can recover the set of parametric equations. It's nothing too new. We're just kind of mashing it up now with vectors. And as I mentioned, we've already encountered a vector-valued function, or a couple different vector-valued functions, when we discussed the vector-valued function for a line, or the vector form of an equation of a line. It looked something like this. So remember back to when we did that, r of t equal to, right, our point on the line plus t times our direction vector. Remember how we did that with lines? That is, this right here is a vector valued function because it takes input, this t parameter, and outputs vectors, which determine where on the line the point is at each parameter value or time value t. And it had this form. So yeah, we've already encountered these. And then one question I'll ask here before I get to, I'll put the answer in the next video, is what curve does the vector valued function r of t equal to a cosine t, a sine t represent? So notice this is two-dimensional. That's okay. We can do two-dimensional curves as well. And the question is, it looks like a 0, 2D, two-dimensional. What does this? So this is sort of a callback to maybe something you saw in Calc 2. We need to be able to recognize parametric equations that look like this. So my x of t is a cosine t. So a is some constant, and y of t is a sine t. Do you recognize this? If not, jump back to chapter 12, please, to the parametric equations section, and look at some of the common parametric equations that you would have worked with in that chapter. It's going to be really important that we can recognize these because we're gonna do a lot with them. So we need to have a good base. So right, go back to chapter 12 if you need to. And then to just end this video, I just want to jump to some interactive figures in our e-text, just to kind of give you an idea of what these vector valued functions look like. So here's a line. This is back in section 13.5 when we looked at lines. So a line, the idea was, remember, that if I change my t value, so here I'm just going to increment my t value, we move along the vector, the direction vector v, and my point changes, but it's always on this line. So input a scalar value t, output this position vector, which tells me where the point is on the line. So that's the idea. But we can have more complicated curves than just lines, and we're definitely going to want to talk about those. They're far more exciting than lines. What about just something general like this? So here we have, I don't know, kind of a little curvy thing here. Kind of loops around. I don't know, maybe it's a part of a roller coaster, something like that. Who knows? But it's the idea is exactly the same. I'm going to input a parameter t, and my output is going to be this vector, which tells me where on the curve the point is at that time value or parameter value t. Right? So I increment t, and my vector moves along and tells me where I am on the curve. You can notice something as I'm doing this, and this is going to turn out to be important, is that it looks like it's actually moving kind of slowly when I increment these t values here around this bend. Right, it's going kind of slowly around the bend. That there's a speed. If we want to think of t as time, there is a speed at which this curve is traced out. So that's going to be something we'll get into later, talk about the speed at which a curve is traced out. And we just move around the curve like this. I'll keep incrementing t, and we move along like that. There's other such curves. How about one like this? This will be one of the examples we work through in this section. Again, I increment t a bit, and I trace out the curve. So this is an object moving according to this curve. We'll see why it has this equation here. So we'll get into more complicated equations like this one. We'll see how to go from this vector valued equation to understanding what the path of this object looks like in 3 dimensions. So we're going to work through that in this example. Again, the idea is I'm inputting a time value or a parameter value, outputting this vector, which tells me where I am on the curve. In this case, it traces out, something that looks about like a Pringles. It's what I think of it, like a chip. They call it the roller coaster curve, but I think of it as a Pringle. Or we could have something like this one. This is a helix. And we'll get into this one as well. Here's a vector valued equation for that. Notice this is in the form with I, j's, and k's. So still vector valued. Here's my x of t, my y of t, my z of t. And again, we input time values and output a vector which tells me where I am at the curve. Here we can really see the time value. So there's one increment. Look at the next increment. Look how far I travel in that one, a little bit farther. Same time, it's time increment, traveled even further in that one. Now I'm slowing down a little bit. I go around the curve, slowing down. See, I barely traveled at all right there. And same increment in time. And so there's some speed at which we travel around this. We're going to want to get into that, especially when we talk about calculus, which, speed. If we have a position, we can take a derivative and recover a velocity. The magnitude of that velocity is our speed. So we'll want to get into that. Okay, I think I've rambled on enough in this video. Again, my point was just to introduce what these vector valued functions are and what we're going to be doing with them. So again, before you start the next video, find out what this vector valued function represents. And again, think of this, you can think of it like a parametric equation. And if you don't recognize it immediately, jump back to chapter 12. I think it's section 1. Sorry if I'm wrong about that, but look through the sections in chapter 12 for parametric equations and see if you can find this anywhere. All right, I'll see you in the next video where I'll answer this question and talk a little bit more deeply about it. I'll see you there.